Hello and good afternoon. We are going to deal with counting principles of probability, and this is the broad outline of the session. We will first introduce why we need these counting principles. Then we will have a problem. We will introduce a problem. Then finally we will discuss all these problems, and we will have conclusion, and then we will have references. Now, why we need? What is the relevance of such a talk? So we have to make decisions under uncertainty, ranging from every sphere of human activity, ranging from whether it is a layman or to a higher end, decision maker in the country like Prime Minister. He has to make decisions under uncertainty. Even at the time of this COVID, the Prime Minister has to take whether he has to extend this lockdown period, or he can stop the process of lockdown. So such decisions under uncertainty has to be taken for everybody, whether he is a decision maker or even he is a layman. So under this uncertainty, how can we make the decisions? A scientific procedure for making decisions under uncertainty needs measurement of this uncertainty, or need measuring this uncertainty, and probability is one of the concepts which enables us to measure this uncertainty. And the basic definition of probability, which says that the probability is the classical definition of probability, which was used prior to 18th century, and which is defining the probability of an event to be as number of favorable cases to the total number of cases. And now the problem arises to us, like how to find out the number of cases of a particular problem. That is the motivation for this talk, and that is the relevance of this session. Unless we are not confronting such a question, how to find the number of cases, we don't have a problem, or we don't have a relevance of this talk in a probability class. Now we will move on to our problem. So before we move on to the problem, we have certain preliminary concepts like what is selection and arrangement. We are saying that when the selection is with, or the selection or arrangement is with replacement or without replacement, what does it mean? So when we are saying that it is with replacement, it means that an individual or an item can be selected or can come to the fray in more than one occasions. Right, for example, can be selected in more than one examples. For example, if you are selecting, suppose we are selecting three individuals from a class, and if it is with replacement, the same person can be selected thrice, right? Or it may be selected, he may be selected in twice. So if a person once selected won't have a chance for being selected in the next time, that will be termed to be as without replacement. And if he has a chance to be selected again, it is with replacement. Then the another concept is order, right? The order of selection. Like for example, if I am selecting A, B, C, if I have selected three alphabets and the selected alphabets are A, B, C, and if A, B, C, B, A, C, and C, A, B are different, it doesn't matter if it matters the order of selection also, then we say that the order matters. So based on, then the other two concept is independence, whether the selection now depends on the other one, and the other one is distinguishability, which are straightforward things. Now based on these two concepts, we have different arenas for selection. And before we further move forward, we have the two basic principles of counting. One is multiplication theorem of counting. It says that if an experiment can be performed in n stages, with n1 outcomes in the first stage, n2 outcomes for the second stage, and so on, then the total number of outcomes of the experiment is given by n1 times, n2 times, etc., nm times. For example, if I can take a doll, if I can go from place A to place B in n1 ways, and place B to place C in n2 ways, then I can go from place A to C in n1 times n2 ways. That is what this multiplication rule says. It is straightforward one. And another associated theorem is addition theorem of probability, which says that if an experiment can be proceed in m ways with N1 outcomes in the first phase, N2 outcome in the second way, and so on. Then the total number of outcomes of the experiment is N1 plus N2 plus etc. Nm. Right, an experiment can proceed in any of the m ways. It can be done in m ways. So that is what this multiplication and addition theorem of counting says. Now we shall come to the problem. Suppose we want to arrange n individuals, A1, A2, etc. An in R slots, or equivalently we want to select R individuals from n individuals. We have the 4 cases. I purposely used bold face letters for the words arrange and select. It is just because arrange in most of the mathematical papers, or in most of the people who are teaching mathematics, probability, basically if you are teaching, if you are a non-statistician, probably you are telling your students that if it is arrangement, you take a factorial or combination, and if it is selection, you take combination. That was the comment people usually make, and that is not essentially the concept is. I want to thrust that concept. That is why I am using the word. I have written arrange and select in bold face letters. In the preliminary classes or in BCom classes, it is used to say that whenever you are confronting a probability problem, where you are asked to find out the number of arrangements, you will go for permutation. And whenever you are asked to find out the number of selection, or we are having a problem of selection, go for the combination. That is what the people usually used to say. That's a wrong notation, and unfortunately that has been used by NCERT in its 9th standard textbook. We are very sad about it, because still people are believing so. Now we have 4 cases coming into play, where is 1 with replacement and the order counts, without replacement and the order counts, without replacement order does not count, with replacement and the order counts. Now we will move on to the first case, with replacement and order counts. So we will have a scenario like A1 can occur more than 1. That is what the replacement says. And the order count says that AI, AJ and AJ, AI are different. Right. So we shall consider the case. That is, it doesn't matter whether AI comes, it matters whether AI comes first or second. So such a scenario. So for the first position, I am having, these are the situations I am going to have. For the first position, I can have A1 or A2 or A3, so on, etc. N. So how many choices I have? I have n choices. So the number of ways for happening the first position is n. Now we shall consider the second position. Again, I have A1, A2, etc. N for the second position. So here also I will have n choices for that one. So by multiplication theorem, the total number of ways to complete the first 2 positions is n times n. Now we will move on to the third position. Here again, we can see that we have n options left behind. That is, it can be A1, A2, A3, A4, etc. n. This is because it matters whether it has been done with replacement or without replacement. So by multiplication theorem, we have n times n choices for filling the first 3 positions. Similarly, if we proceed further, and for the nth position, we will have, similar to the above discussions, we will have n choices, and we can choose any of these n choices. As we have n choices, it is n. So the total number of ways is n times n, that is equal to n raised to r. That is the first case. We are coming to the end of the first case, when the selection or the arrangement is done in such a way that there is replacement and the order counts. We have n raised to r cases. Now we will move on to the second case, without replacement and order counts. So that is what means that AI can occur only once. Once AI is selected, no more AI is coming to free. And AI, AJ and AJ, AI are different. Now for the first position, as mentioned, as discussed in the first case, I can have n choices, A1, A2, A3 or etc. and assume that AI comes in. So AI comes in, I have n choices for this AI. AI can be A1, A2, etc. AI, and I have n choices. Now, let us come to the second point. I can have anything A1, A2, A3, etc. AN, but AI cannot come because AI has already occurred. So now it is the turn of AJ. Let us assume that AJ has happened. Now I can have A1, A2, etc. AN, but not AA. So I have N1, N minus 1 choices. So beyond with us. And assume that the second position AJ occurs. Now let us come to the third point. So when it comes to the third point, I can have A1, A2, A3, etc. AN may happen, but AI and AJ does not happen. Let AK comes to the post. So how many choices I can have? A1, A2, etc. AN. So N, but not AY and AJ. So N minus 2 choices I will have. So this is the situation. Now proceeds like that. I can have for the rth position I can have n minus r plus 1. So total in this is the situation I will have n into n minus 1 into n minus 2 into etc. n minus r minus 1. This can be summarized to be as n factorial divided by n minus 1 n minus r factorial. So we will discuss the further two cases in the next session. Okay, thank you for your patient listening. Thank you.